Dark energy is one of the great mysteries of the universe. What exactly is it? Why is it so relevant to modern cosmology? To understand it, it is essential to know that dark energy represents about 70% of everything that exists in the cosmos. Yet, despite its enormous influence, it is practically undetectable. How can something so omnipresent be so elusive? Throughout history, we have looked to the sky for answers about our place in the universe. Stars, planets, and galaxies have fascinated humanity for centuries. However, as we advance in our understanding, we have encountered a puzzling fact. The universe is not only expanding, but it is doing so at an ever-increasing rate. What could be driving this acceleration? Recent research suggests that this mysterious force could be dark energy, although its nature remains an enigma. Imagine a universe in which expansion stops, a universe where gravity manages to overcome the force of this dark energy. But why doesn't that happen? Why, instead of slowing down, does the universe seem to be accelerating its expansion? This is one of the most intriguing questions that astronomers and physicists are trying to answer. In a cosmos where visible matter is just a small fraction of what exists, dark energy becomes the undisputed protagonist of the universe's story. The search for answers about dark energy not only leads us to question its nature, but also its origin. Where does it come from? How did it form in the early universe? As scientists attempt to unravel these secrets, they face the reality that dark energy does not emit light, radiation, or anything we can measure directly. This makes it one of the greatest cosmic enigmas. Darkness can be a frightening concept, but in the case of dark energy, it serves as a reminder of how little we truly understand about the universe. And here arises another fascinating question. If dark energy is so powerful, why can't we see its effect more directly? As telescopes and technologies advance, we realize that, although we cannot see it, its influence is everywhere. Evidence of this is how it affects the formation and distribution of galaxies. Galaxies are not simply floating in space, they are in constant interaction, and dark energy plays a crucial role in their evolution. So what does this mean for the future of the cosmos? The answer to this question is equally intriguing and terrifying. Depending on how dark energy behaves, the universe could continue to expand forever, leading to a fate where galaxies drift apart until they become invisible to one another. Or, in an even more dramatic turn, a big rip could occur where the very structure of space-time tears apart. Dark energy is undoubtedly one of the greatest mysteries facing science today. Our understanding of it will not only change our view of the universe, but could also redefine our place within it. As we advance in our exploration of the cosmos, dark energy reminds us that while we have made great progress, there is still much to discover. Are we ready to face the secrets that the universe holds? The answer could change everything. Dark energy is one of the great mysteries of the universe, and its relationship with dark matter is a topic that has intrigued scientists for decades. What exactly is dark matter? It is a form of matter that we cannot see or detect directly. But we know it exists due to its gravitational influence on galaxies and other celestial objects. But could it be that dark energy and dark matter are connected in some way? This is the dilemma we face. Although both concepts are fundamental to our understanding of the cosmos, the connection between them remains an enigma. Some theories suggest that they could be two sides of the same coin, but the lack of concrete evidence leaves us in uncertainty. Could dark energy be the engine that drives dark matter? Or perhaps does dark matter act as an anchor that stabilizes dark energy in the vast fabric of the universe? The key to understanding this relationship may lie in how both influence the expansion of the universe. Dark matter, although invisible, acts like glue that holds galaxies together, while dark energy seems to be pushing the universe towards accelerated expansion. Imagine a balloon being inflated. Dark energy is the force that makes it grow, while dark matter would be the air that allows the balloon to maintain its shape. But what happens when we try to unravel the origin of each? Dark energy, in its essence, is a phenomenon that has emerged in a constantly changing universe. But where does it come from? Unlike dark matter, which may be related to yet undiscovered subatomic particles, dark energy seems to be even more elusive. Scientists have proposed various theories, from Einstein's cosmological constant to more complex concepts like quintessence, but none have managed to provide a definitive answer. So what does this tell us about the nature of dark energy? The lack of visibility of dark energy adds another layer of mystery. Unlike celestial objects that we can observe through telescopes, dark energy does not emit light or detectable radiation. This raises the question, how can we study something we cannot see? The answer lies in indirect observation. By studying the expansion of the universe and the distribution of galaxies, scientists have been able to infer the existence of dark energy, but much remains to be discovered. Is it possible that we will ever have a complete picture of its nature? The influence of dark energy on the expansion of the universe is another fascinating aspect. Currently, we know that the universe is not only expanding but doing so at an accelerated rate. Why is this happening? Some scientists believe that dark energy is responsible for this acceleration, acting as a repulsive force that challenges gravity. But is it possible that this acceleration is not constant? Perhaps it could change over time. As we explore this enigma further, we encounter the question of how much dark energy exists in the universe. Current estimates suggest that approximately 70% of the universe is composed of dark energy. But how can scientists be so sure of this if they cannot measure it directly? The answer lies in how dark energy affects the structure of the universe. Through mathematical models and simulations, researchers have been able to reach this conclusion, but it remains a topic of debate. The homogeneity paradox is another intriguing aspect of this discussion. Dark energy appears to be uniformly distributed throughout the cosmos, raising questions about its behavior. Why is it so constant and uniform? Are there hidden forces controlling its distribution? These questions are essential for understanding how dark energy interacts with the rest of the universe. Some scientists are investigating the role of gravitational waves in relation to dark energy. These waves, which are disturbances in space-time caused by massive cosmic events, could hold crucial clues about the nature of dark energy. Could these waves, which have been detected by experiments like LIGO, offer a new way to study such an elusive phenomenon? The possibility that dark energy and gravitational waves are interconnected is a topic gaining attention in the scientific community. The influence of dark energy also manifests in the formation and distribution of galaxies on a large scale. It has been observed that its action can alter how galaxies cluster and distribute in the universe. Could it be that dark energy is shaping the cosmos in ways we do not yet fully understand? This question is fundamental to our understanding of the evolution of the universe. As we explore the future of the cosmos, dark energy becomes a determining factor. Depending on how it behaves, the universe could continue to expand indefinitely, or, in the worst-case scenario, experience a cataclysm known as the Big Rip. Is the universe destined for an explosive end, or will it slowly fade into darkness? These are questions that cosmologists strive to answer as they attempt to decipher the secrets of dark energy. The quantum vacuum is another area where connections with dark energy have been proposed. It has been suggested that this energy could be related to vacuum energy, a concept that challenges our understanding of physics. But what does this really mean? The idea that the vacuum is not truly empty but filled with constantly fluctuating energy opens the door to new ways of thinking about reality itself. In the quest to understand dark energy, scientists have explored the possibility that its behavior has changed over time. The theory suggests that in the early moments of the universe, dark energy may have had different properties than those we observe today. What implications would this have for our understanding of the history of the cosmos? Every answer we find generates new questions, making this quest even more exciting. The density problem is another enigma we face. Theoretically, models predict that there should be overwhelming amounts of vacuum energy, far more than we actually observe. Why is there such a large discrepancy between theory and reality? This question is crucial for solving the puzzle of dark energy and its role in the universe. Finally, The link to hidden dimensions is one of the most intriguing theories. Some scientists suggest that dark energy could be a byproduct of additional dimensions that we cannot perceive. If this is true, what other realities might be existing around us, invisible to our senses? The idea that dark energy could be just the tip of the iceberg of a more complex reality is fascinating and leads us to question our understanding of the universe as a whole. As we continue to explore these mysteries, it becomes clear that the relationship between dark energy and dark matter is a fertile field for research. Although we do not yet have definitive answers, each discovery brings us one step closer to unraveling the secrets of the cosmos. What other mysteries does the universe hold for us? The search for answers continues, and with it, the promise of new and exciting discoveries. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey. Where does dark energy come from? It is a question that has intrigued scientists and cosmology enthusiasts alike. In the vast universe we inhabit, the origin of this mysterious force remains an unsolved enigma. How can something so omnipresent have no clear origin? What does this tell us about the beginning of everything? Since the Big Bang, the universe has been in constant evolution. However, dark energy seems to have begun playing a crucial role at a later stage of this evolution. Why did it start to manifest at a specific moment and not before? Current theories suggest that, in its early moments, the universe was dominated by other forces and energies. However, the transition to a cosmos where dark energy governs is a mystery. What happened in those early moments for dark energy to emerge as one of the main forces of the universe? One of the most puzzling aspects of dark energy is its nature. We cannot see it, we cannot touch it. And yet it seems to be responsible for the acceleration of the universe's expansion. How can something that is not detectable through conventional methods influence the structure of the cosmos so profoundly? Imagining that there is a force acting over vast distances that we cannot directly observe can be daunting. How can we accept its existence without tangible evidence? The way dark energy relates to the rest of the universe also raises fascinating questions. Could it be that this energy is connected to other phenomena we observe? Some scientists have speculated that perhaps dark energy is not just a form of energy, but also contains clues about the very nature of the universe. Could it be that by understanding the origin of dark energy, we are also unraveling other cosmic secrets? The theories about its origin are varied and often speculative, from the possibility that it is a form of vacuum energy to the idea that it could be related to hidden dimensions. The options are numerous. Is it possible that there are laws of physics that we have yet to discover, which would help us understand how this energy arose? The nature of the universe seems to be full of surprises, and every answer we find raises new questions. Throughout history, scientists have attempted to create models that explain how dark energy formed and what its role is in the universe. However, these models often face significant challenges. Why do our best theories fail to provide a clear answer? Is it possible that we are looking in the wrong direction? Moreover, the lack of concrete evidence about the origin of dark energy leads us to reconsider our understanding of physics. Are we facing a phenomenon that cannot be explained by the laws we know? If dark energy is a manifestation of a universe we do not fully understand, what other truths might be hidden in plain sight? Every day, scientists strive to unravel this enigma, but the path is arduous and full of obstacles. The fact that dark energy is present in approximately 70% of the universe also raises questions about its origin. How is it possible that such a significant amount of energy is so elusive? The idea that we might be under the influence of this invisible force is undoubtedly unsettling. What does this mean for our understanding of the cosmos and our place in it? As we explore the possibility that dark energy has a different origin, other questions arise. Could it be related to events that occurred in the early universe before galaxies began to form? The history of the universe is rich in extraordinary events. And it is possible that dark energy has roots in these fundamental moments. What secrets of the past could be revealed if we manage to understand how it originated? On the other hand, dark energy could be a reminder of the vastness of the universe and how little we truly know. Every discovery we make opens new doors, but also reveals the vastness of our unknown. Are we prepared to accept that some answers may lie beyond our current understanding? Humility in the pursuit of knowledge is essential, and dark energy could be one of those mysteries that teach us to look at the cosmos with wonder and curiosity. As we move into the 21st century, technology and observational methods are advancing rapidly. Will future generations of scientists unravel the mystery of the origin of dark energy? The history of science is full of surprises and unexpected discoveries, and it is possible that, at some point, the answer to this question will be revealed. However, until that happens, the search continues. Dark energy, with its elusive nature and monumental impact on the universe, teaches us about our limitations and the beauty of the unknown. Ultimately, its origin remains hidden, but its study drives us to keep inquiring. What other mysteries await us in the vast universe we inhabit? The quest for answers about dark energy is just a part of a much larger and more astonishing journey. What makes dark energy a true enigma? The intriguing aspect of this phenomenon is that despite occupying approximately 70% of the universe, we cannot see it. It's as if it were a shadow stretching across the cosmos, preventing the light of our understanding from reaching it. But why is it so difficult to detect something that seemingly constitutes such a significant part of our reality? The answer lies in its very nature. Dark energy does not emit light or radiation that we can measure. Therefore, it becomes a completely invisible mystery, a challenge for scientists and a fascinating topic for the curious. The invisibility of dark energy raises intriguing questions. What does it mean for something to be undetectable through traditional methods of observation? In science, the ability to observe is fundamental to understanding. However, dark energy forces us to think beyond the limits of our senses. Could it be that there are forms of knowledge we have yet to develop? Or perhaps there are aspects of reality that elude our current understanding? This duality between the known and the unknown is what makes dark energy one of the greatest cosmic enigmas. Astronomers have attempted to unravel this mystery through the observation of galaxies and their behavior. How is it possible that the universe is expanding at an accelerated rate? And what role does dark energy play in this expansion? Galaxies are moving away from us, and studies show that this speed increases over time. But here arises a new question. If dark energy is behind this acceleration, why can't we detect it directly? The answer lies in its subtle nature and the way it interacts with visible matter. Imagine for a moment that the universe is like a huge balloon being inflated. As the balloon expands, galaxies move apart from one another. But what is inflating that balloon? Dark energy, being invisible, acts as an agent pushing outward, increasing the distance between celestial bodies. However, this action is so delicate that it leaves no obvious traces for us to follow. How can we measure something that has no tangible form? The nature of dark energy also raises questions about its homogeneity. Despite its invisibility, it seems to be evenly distributed throughout the universe. But how is it possible for something so elusive to have such a constant distribution? Homogeneity challenges our notions of how forces behave in the cosmos. It invites us to consider the possibility that there are principles behind its action that we have yet to discover. Delving a little deeper, we find that this dark energy not only affects the expansion of the universe, but also impacts the formation and distribution of galaxies. What implications does this have for the large-scale structure of the cosmos? Dark energy could be influencing how galaxies cluster, altering the very fabric of the universe itself. However, how can we verify an influence that we cannot see? This is the dilemma faced by scientists, who seek answers in the silence of darkness. The invisible nature of dark energy leads us to explore the concept of vacuum, a place that seems completely devoid of matter. But what is in the vacuum? Some scientists believe that dark energy is related to vacuum energy, a fascinating concept that challenges our understanding of nothingness. Is it possible that forces exist in the vacuum that we have yet to identify? The idea that the vacuum could be filled with energy is both perplexing and intriguing. Although dark energy is a significant player in cosmology, its nature remains a mystery. Why, in the history of the universe, did it begin to dominate at this particular time? Is there a reason behind its emergence at this specific moment? The search for answers leads us to question not only our view of the cosmos, but also time itself. Scientists have proposed various theories to explain this phenomenon, but the truth is that we are still far from a definitive answer. Dark energy could be a quintessence field, suggesting that its influence is not constant but changes over time. But how can we validate this hypothesis if we cannot observe dark energy directly? It is a challenge that requires innovation and an open mind to explore new frontiers in science. Meanwhile, the density paradox confronts us with another enigma. Theoretical models suggest that the vacuum could contain immense amounts of energy, far more than we observe in reality. Why this discrepancy? What does it tell us about our understanding of the universe and its laws? Such questions push us to reevaluate our theories and seek new ways to understand our surroundings. As we explore these mysteries, we must remember that our quest for knowledge is an ongoing journey. Dark energy, with its elusive nature, challenges us to keep asking, to keep searching. Each discovery brings us a little closer to the truth, but it also leaves us with more questions. Science is an endless path, where each answer opens the door to new mysteries. So as we contemplate the vast universe and its secrets, dark energy reminds us of how little we truly know. It invites us to continue exploring, to keep probing the unknown. The search for answers about this phenomenon is not only crucial for understanding the cosmos, but also for comprehending our place within it. Dark energy may be invisible, but its influence is undeniable. And its mystery is a powerful engine of curiosity that propels us into the future. The accelerated expansion of the universe is one of the most intriguing phenomena posed by modern cosmology. But what does it really mean that the universe is expanding faster and faster? To understand it, we must imagine the universe as a balloon being inflated. As the balloon fills with air, the points drawn on its surface move apart from each other. Now imagine that, in addition to inflating, this balloon also starts to accelerate its expansion. That is exactly what is happening with our universe, and dark energy is responsible for this process. But where does this dark energy that drives this acceleration come from? Although scientists have proposed various theories, the truth is that we still do not have a definitive answer. Dark energy could be a form of energy that fills empty space, a mysterious field that acts in opposition to gravity. But why now? Why did the universe begin to expand rapidly a few billion years ago and not before? These questions lead us to explore the very nature of dark energy. One of the most surprising features of dark energy is its effect on galaxies. Imagine that galaxies are boats in an ocean that is expanding. As the ocean stretches, the boats move away from each other. This is what happens with galaxies in space. Dark energy acts like an invisible engine that pushes them apart, increasing the distance between them. But what implications does this have for the future of the universe? Could it be that, thanks to dark energy, the universe will expand forever, or even that this process of creating new galaxies will repeat in an endless cycle? The accelerated expansion is not only a phenomenon we observe, but also an enigma that challenges our understanding of the laws of physics. What happens to gravity in this context? Gravity, which normally pulls galaxies together, seems insufficient to counteract the push of dark energy. Does this mean our theories about gravity are incomplete? Or are we facing a new type of force that we have not fully understood? As we ponder the nature of dark energy, one of the most fascinating theories that has emerged is the idea that this energy could be related to quantum vacuum. According to this perspective, the vacuum is not an empty space at all, but a sea of subatomic particles that constantly appear and disappear. Could it be that dark energy is a manifestation of this quantum vacuum, a kind of latent energy that fills the cosmos? Although this idea is intriguing, we have not yet found evidence to support it as the expansion of the universe continues. New questions also arise. If dark energy is driving this acceleration, could there be changes in its behavior over time? Some scientists suggest that dark energy might not be constant but could change in intensity. What would happen if one day its effect weakened? Could the universe begin to contract instead of expand? These questions lead us to consider different scenarios about the ultimate fate of the cosmos. One of the most puzzling aspects is the amount of dark energy that seems to exist. Approximately 70% of the universe is composed of this mysterious energy, but how can we be sure it really exists? Unlike visible matter that we can observe through telescopes, dark energy does not emit light or radiation. Its presence is inferred from the effects it has on the expansion of the universe. Is it possible that there are more hidden secrets in the cosmos that we have yet to discover? The homogeneity paradox also adds a layer of complexity to the mystery. Dark energy appears to be evenly distributed in space, raising questions about its origin and nature. If dark energy behaves so uniformly, does this mean it has a deeper connection with the structure of the universe? Or is it an isolated phenomenon that we simply do not understand? As science advances, researchers are seeking answers through new technologies and observation methods. Gravitational waves, for example, have opened a new window to the universe. Could these waves contain clues about the nature of dark energy? If we manage to detect and analyze these waves, we could uncover hidden secrets about how dark energy interacts with the fabric of space-time. In this journey of exploration, the possibility that there are hidden dimensions influencing our understanding of dark energy is also raised. Some theories suggest that we might be experiencing effects from additional dimensions that we cannot directly perceive. What implications would this have for our understanding of the universe and its expansion? Could it be that dark energy is a manifestation of something much larger and more complex than we have imagined? As we reflect on the accelerated expansion of the universe, it is essential to remember that this is a constantly evolving field. Each discovery raises new questions and opens new avenues for research. The story of dark energy is a story of mystery, uncertainty, and wonder, as scientists continue to explore the cosmos and unravel its secrets. It is likely that each answer will reveal even more questions. Are we prepared to face the mysteries that still await us? The search for the truth about dark energy is a journey that is just beginning, and we are all part of this cosmic adventure. Have you ever wondered how much dark energy exists in the universe? Scientists estimate that approximately 70% of our cosmos is composed of this mysterious form of energy. But how do they arrive at that figure? What does it really mean? The answers to these questions are not only fascinating, but also reveal a puzzle that has baffled astronomers for decades. To begin with, let's talk about the amount. 70% is an astonishing figure. But what is even more surprising is that we have no direct way to measure dark energy. Imagine trying to weigh something you cannot see or touch. Sounds complicated, right? That's how scientists feel when trying to quantify this energy. All we have are indirect observations and theories that attempt to explain its existence. How did they arrive at that 70% estimate? Cosmologists use data about the expansion of the universe and the distribution of galaxies to make their calculations. By observing how galaxies move and how they are receding from each other, they have deduced that there is something more at play than just gravity. This something more is what we call dark energy. But what about visible matter and dark matter? Where do they fit into this cosmic puzzle? Visible matter, which includes stars, planets, and galaxies, accounts for less than 30% of the universe. Dark matter, which does not emit light or radiation, constitutes another important part, but even adding both together we fall short. Dark energy is what fills the void and tips the cosmic balance. But why does it behave this way? Why does it seem to be so abundant? An intriguing aspect is the relationship between dark energy and dark matter. Dark matter influences the formation of galaxies, while dark energy affects the expansion of the universe. Could these two forms of matter and energy be connected in some way? Some scientists believe they might be two sides of the same coin, but so far we have not found the proof to confirm this theory. Imagine a universe where dark energy did not exist. The expansion of the universe would slow down, and galaxies might move closer to each other instead of drifting apart. In this alternative scenario, the cosmos would be a very different place, perhaps a place where galaxies as we know them would not exist. This leads us to wonder, what would happen if dark energy were less abundant than we think? Could that change the future of the universe? The dilemma of the amount of dark energy also raises questions about the very nature of the vacuum. Some theoretical physicists suggest that the vacuum, far from being simply nothing, could be filled with energy that we have not been able to detect. But why have we not been able to measure this vacuum energy? Are we looking in the wrong place? The paradox intensifies when we consider the energy density that models predict. According to quantum physics, we should observe an immense amount of energy coming from the vacuum, far more than what we see in reality. So why is the amount of dark energy that seems to exist so low compared to what calculations suggest? This is a puzzle that has scientists scratching their heads. And it's not just about numbers. The way dark energy interacts with the structure of the universe is equally perplexing. In regions where dark energy is more intense, galaxies appear to be dispersed. Could it be that dark energy is influencing how galaxies cluster and distribute throughout space? This question leads us to explore more deeply the very fabric of the cosmos. Imagine that every time we look at the sky, we are observing not only stars and planets, but also the impact of dark energy on our own existence. Without it, the universe as we know it would not exist. But will it ever be possible to discover its true nature? Or perhaps dark energy is a phenomenon destined to remain a mystery. At the end of the day, the enigma of the amount of dark energy is tied to our understanding of the universe. Each new investigation, each discovery brings us one step closer to unraveling this mystery. However, the answer may lie beyond our capacity for comprehension. Could we even be dealing with a form of energy that challenges the laws of physics as we know them? These questions are just the beginning of a journey that could redefine our view of the cosmos. In summary, dark energy, which represents approximately 70% of the universe, remains one of the greatest enigmas of modern cosmology. As scientists continue to investigate and seek answers, we find ourselves facing a fascinating landscape that invites curiosity and reflection. With each new discovery, we open the door to a universe of possibilities, where the mysteries of dark energy continue to await revelation. Dark energy is a phenomenon that leaves us with more questions than answers. What causes this mysterious form of energy to be distributed so uniformly throughout the universe in a cosmos that at first glance seems chaotic and full of variations? The homogeneity of dark energy is perplexing. How is it possible that something so invisible and ethereal can influence the structure and behavior of the universe in such a subtle yet powerful way? To understand this enigma, it is essential to consider how dark energy behaves on a large scale. While galaxies and stars are distributed irregularly, with clusters and voids, dark energy seems to be present in every corner of space in a way that challenges our intuition. Why doesn't this energy concentrate in certain areas of the universe or distribute unevenly like other elements? The answer to this question may lie in the very nature of dark energy. Imagine for a moment that dark energy acts as a cosmic balancing agent. While gravity tends to attract matter, dark energy could be pushing, promoting a uniform expansion. But why should it be this way? If we consider that dark energy represents approximately 70% of the total universe, its influence is undeniable. However, its nature remains a mystery. Is it a constant or variable field? Could it be that in some parts of the universe its effect is stronger than in others? As scientists study the homogeneity of dark energy, they face a dilemma. Current theory suggests that dark energy acts uniformly on cosmic scales, but that does not explain why we do not see fluctuations in its presence. What if, somewhere in the universe, dark energy behaves differently? It could be that there are regions where its effect is more intense, but we simply have not been able to observe them. The lack of concrete data makes these questions even more intriguing. Moreover, the uniform distribution of dark energy raises a dilemma about the origin of structures in the universe. If dark energy is present everywhere, how is it possible that we see groupings of matter? Galaxies, clusters, and superclusters seem to challenge the idea of energy acting uniformly. Is it possible that dark energy interacts in some way with matter that we do not yet understand? The answer to this question could change our perspective on the universe. Current models suggest that dark energy is a fundamental feature of the universe since its creation. However, looking back into the past presents us with a puzzle. How could dark energy have been present in the early universe and still maintained such remarkable homogeneity? It could be that in the first moments after the Big Bang, dark energy behaved differently, allowing the first cosmic structures to begin to form. On the other hand, we cannot ignore that this phenomenon has implications for how we perceive time and space. The homogeneity of dark energy could influence how the universe expands, but what does this mean for our future? If dark energy continues to dominate, the universe could keep expanding indefinitely. However, for this to happen, that uniformity must be maintained. Is it possible that dark energy changes over time, altering its distribution and consequently the fate of the cosmos? In this context, the question of homogeneity also becomes a matter of scales. On small scales, dark energy may seem less relevant, but on cosmic scales, its influence is undeniable. The curiosity to understand how this energy manifests at different scales leads us to explore new horizons in cosmic research. Could there be ways to measure dark energy in different parts of the universe that reveal its true nature? It is astonishing to think that in a universe full of mysteries, dark energy remains one of the most elusive. As we continue to explore the cosmos, each discovery brings us closer to unraveling this enigma. The homogeneity of dark energy could be an indicator of fundamental principles of physics that we have yet to fully understand. What new theories will emerge as we advance in our quest for answers? Thus, the question of the homogeneity of dark energy is not only a challenge for scientists, but also invites us to reflect on our place in the universe. What does it mean for us to know that a large part of the cosmos is governed by something we cannot see or touch? This mystery reminds us that, although we believe we know much about the universe, vast unexplored territories still await us. The search for answers about dark energy and its homogeneity is a journey that combines science, curiosity, and wonder. Each new observation could be the key to uncovering the hidden truths of the cosmos. So, as we look up at the starry sky, let us not stop asking, what secrets does dark energy hold for us, and how will it affect our understanding of the universe in the future? Dark energy, that intriguing concept that seems straight out of a science fiction novel, may have fascinating connections with gravitational waves. What exactly are gravitational waves? They are distortions in space-time that occur when massive objects, such as black holes or neutron stars, collide. If we can detect these waves, could we open a window to a new understanding of dark energy? Imagine that by observing how these waves propagate through the universe. The influence of dark energy is subtly revealed. Could it be that gravitational waves, as they travel through space, interact with this enigmatic force in some way? Some scientists believe that by studying gravitational waves, we could gain clues about the nature of dark energy. But how are these two seemingly disparate things related? Gravitational waves are the echoes of distant cosmic events, and their study allows us to glimpse what happens in the depths of the cosmos. However, dark energy, being such an elusive phenomenon, raises more questions than answers. Why have we not been able to detect its presence directly? Is it possible that the interaction between gravitational waves and dark energy is so subtle that we have not yet fully understood it? One of the most fascinating theories is that gravitational waves could act as a bridge between the visible world of matter and the mysterious dark energy. Could it be that these waves are telling us something we have yet to hear? If we manage to decipher the message, we could obtain crucial information about the accelerated expansion of the universe and the role dark energy plays in this process. Consider the case of black hole collisions. When two black holes merge, they generate gravitational waves that travel through the cosmos. Along the way, these waves may experience variations in their shape, and some scientists suggest that these variations could be influenced by dark energy. But how can we test this hypothesis? Imagine that through gravitational wave detectors, an unusual pattern in the data is observed. This could be a signal that dark energy is somehow affecting these waves. If this is true, we could be on the brink of a monumental discovery that would change our understanding of the universe. The key lies in ongoing research and technological advancements that allow us to observe increasingly subtle phenomena. However, this is not as straightforward as it seems. Dark energy is extremely difficult to study due to its invisible nature. Unlike other forms of energy that we can measure directly, dark energy does not emit light or radiation. This poses a monumental challenge for scientists seeking to unravel its secrets. But could it be that gravitational waves are the path to a new era of discovery? Theoretical physicists are exploring models that relate gravitational waves to dark energy, searching for patterns that help us understand this connection. But how long will it take to reach a definitive answer? Science progresses slowly, and often the most important discoveries arise from perseverance in the face of multiple failures. Yet, every small advance brings us closer to solving this mystery. As we move forward in this quest, it is essential to remember that dark energy represents about 70% of the universe. This means that, although we cannot see it, its influence is omnipresent. What would our cosmos be without this mysterious force? It could be that the answer to this enigma is hidden in the gravitational waves we are still learning to listen to. Some believe that the study of gravitational waves could revolutionize cosmology as we know it. If we manage to establish a solid connection between these waves and dark energy, we could unravel not only the behavior of the universe but also its long-term fate. Are we prepared to face the impact of such a revelation? Dark energy remains one of the greatest enigmas of modern science, and the role that gravitational waves could play in its understanding is an exciting field of research. As we continue to investigate, each discovery in this area could be a step toward resolving questions that have fascinated humanity for centuries. Scientists continue to work tirelessly in this pursuit, and although spectacular discoveries are not made every day, each small milestone brings us closer to a deeper understanding of the universe. Who knows what unexpected revelations the future holds? Each new advance in the detection of gravitational waves could be the key to understanding the very essence of dark energy. So, as we continue to explore the mysteries of the cosmos, let us remember that every question we ask brings us a little closer to the truth. The connection between gravitational waves and dark energy is not just a scientific enigma. It is a reminder that in the pursuit of knowledge, every answer leads us to new questions. Are we ready to keep exploring? The influence of dark energy on galaxies is a fascinating topic that leads us to ask, how does this mysterious form of energy affect the structure of the universe? When we observe the cosmos, we notice that galaxies are not distributed uniformly. Some regions are teeming with them, while others appear desolate, almost empty. But what force drives this astonishing variety? Astronomers have discovered that dark energy plays a crucial role in the formation and distribution of galaxies. However, the question remains, in what way exactly? As the universe expands, dark energy acts as a repulsive force, pushing galaxies apart. This causes galaxies in certain areas where gravity is less intense to tend to separate more rapidly. Thus, dark energy could be responsible for some galaxies becoming increasingly distant from one another. But what does this mean for the future of galaxies? Imagine that dark energy continues to dominate the expansion of the universe. In that case, we might ask again, what will happen to the galaxies we know today? It is possible that in the distant future, many of them will become lonely islands far from their cosmic neighborhood, with no possibility of interacting with other galaxies. This scenario is unsettling but also fascinating, as it invites us to reflect on the solitude of the universe. Dark energy might also be behind another intriguing phenomenon. The formation of large-scale structures. Galaxies not only cluster into groups but also form filaments and voids that weave a vast cosmic web. Why are they distributed this way? The influence of dark energy could be the thread that connects these structures, guiding them through the vast canvas of the universe. As scientists investigate more about dark energy, even more intriguing questions arise. For example, could dark energy be responsible for galaxies behaving differently depending on the region of the universe they are in? Some researchers suggest that in certain areas dark energy might have a more pronounced effect, thereby altering how galaxies form and evolve. Are we witnessing a phenomenon that varies from one place to another in the cosmos? As we delve into these mysteries, we must also consider the role of gravity. Gravity, which has been the dominant force in the formation of large-scale structures for most of the universe's history, now seems to be in a constant struggle with the accelerated expansion caused by dark energy. How do these two forces interact? Could it be that dark energy is creating a delicate balance, allowing galaxies to continue forming but under a completely different regime? In addition to the formation and distribution of galaxies, dark energy could influence their evolution. How does its expansion affect the life of a galaxy? As galaxies separate more and more, the amount of dark matter and gas available to form new stars might decrease. This leads us to wonder, are we witnessing the end of the stellar era in the universe? If dark energy continues to dominate, we may be on the threshold of a future where galaxies become darker places, where star formation is a distant memory. As we explore these ideas, we should also consider the effects of dark energy on colliding galaxies. What happens when two galaxies meet in the path of their expansion? The answer could be surprising. Dark energy may amplify or mitigate gravity in these interactions, affecting how galaxies merge and transform. This phenomenon could give rise to new galactic structures, challenging our understanding of how galaxies form and evolve. Observing these interactions is crucial for unraveling the role of dark energy. With advances in technology and improvements in telescopes, scientists can observe distant galaxies and analyze their behavior in this context. As they collect data, new questions arise. Could these studies reveal patterns that help us better understand dark energy and its impact on the cosmos? With each discovery, we find ourselves closer to solving the enigma of dark energy. However, much remains to be explored. The influence of dark energy on galaxies is just one piece of a much larger cosmic puzzle. As we continue to investigate, we realize that each answer generates new questions, and the journey toward understanding the universe is, in itself, a fascinating mystery. Ultimately, the relationship between dark energy and galaxies invites us to reflect on our own existence in the vast cosmos. What does it mean to be part of an expanding universe where dark energy plays such a crucial role? As we continue to explore and discover, it is important to remember that each answer we find brings us a little closer to unveiling the secrets of the universe and understanding our place within it. The quest for answers about dark energy and its influence on galaxies is undoubtedly a journey that has only just begun. What is the future of the cosmos? This is one of the most fascinating questions we can ask when discussing dark energy. Let's imagine a universe in which dark energy continues to expand. What will happen to galaxies, to stars, and ultimately to ourselves? As dark energy continues to play a crucial role in the expansion of the universe, scientists have formulated various theories about how this phenomenon might affect our cosmic destiny. One of the most intriguing possibilities is the idea that the universe could expand forever. This means that galaxies would continue to move away from each other, and eventually, those that are farther away would become invisible to us. Over time, we could find ourselves in a dark universe where the stars... What if I told you that the vacuum could be a source of unimaginable energy? Although it sounds strange, there are scientists who believe that dark energy could be related to the concept of the quantum vacuum. But what exactly is the quantum vacuum? At first glance, we might think that the vacuum is simply space without matter, but in the quantum world, things are much more complicated. In this realm, the vacuum is not an empty place, but a turbulent sea of virtual particles that appear and disappear in fractions of a second. How is all this connected to dark energy, and what does it mean for our understanding of the universe? The idea that the vacuum can contain energy has been the subject of great study. Imagine that instead of being a simple space with nothing, the vacuum is filled with potential energy. Physicists have theorized that this vacuum energy could be responsible for the acceleration of the universe's expansion. But why can't we see it? The answer is that this energy is extremely subtle and does not manifest directly. How can something so omnipresent and yet so invisible have such a profound impact on the cosmos? Delving deeper into this idea, it is crucial to understand that dark energy and the quantum vacuum could be two sides of the same coin. Some researchers have proposed that dark energy could be the result of fluctuations in this quantum vacuum. But if this is true, why have we not been able to measure it directly? The answer lies in the very nature of dark energy, which does not lend itself to conventional observation methods. It's like trying to catch water in your hands. No matter how hard you try, it always slips away. The question then is, can dark energy be manipulated in any way? Some scientists believe that if we can understand how these vacuum fluctuations work, we could open the door to almost infinite energy sources, but this is where we enter slippery ground. Quantum mechanics tells us that reality at the subatomic level is very different from what we experience in our daily lives. Is it possible that dark energy is simply a manifestation of quantum laws that we have yet to fully understand? A fascinating dilemma is that, although the vacuum seems empty, events occur within it that challenge our intuition. For example, in the quantum vacuum, particles can emerge and annihilate in an instant. This leads us to wonder, could there be properties of dark energy that we have yet to discover due to our limited understanding of the vacuum? Imagining a universe where the vacuum plays an active role in the structure of the cosmos is both exciting and unsettling. Some scientists have suggested that, in the early moments of the universe, dark energy may have behaved very differently than we observe today. This raises a series of questions. If dark energy has changed over time, what does that tell us about its nature? Could it be that as the universe evolves, dark energy does too, transforming into something we cannot yet predict? An intriguing perspective is that the quantum vacuum is not just a field of energy, but it could also be related to additional dimensions. Some theories suggest that there are more dimensions in the universe than we can perceive. If this is the case, dark energy could be a phenomenon that manifests due to those hidden dimensions. What implications would this have for our understanding of space and time? Most current theories about dark energy are based on complex mathematical models, which have had notable success in predicting certain cosmic phenomena. However, the connection between vacuum energy and dark energy remains one of the most intriguing and challenging questions in modern cosmology. Could it be that the vacuum, in its essence, is a portal to a new way of understanding the universe? One aspect that deserves attention is the fact that despite the importance of dark energy, its study is complicated by the lack of direct data. The nature of dark energy makes it almost impossible to create a laboratory experiment that reproduces it. This leads to a fundamental question. Are we doomed to live with this mystery, or is there a path to understanding? Meanwhile, the scientific community continues to explore various theories and experiments that could shed light on these enigmatic facts. Dark energy is a fascinating concept that has captured the imagination of scientists and cosmic enthusiasts alike. However, have you ever considered what was happening in those early moments of the universe? Right after the Big Bang? At that time, the cosmos was a very different place from what we know today. It is said that dark energy may have behaved very differently, leaving us wondering, how could such a mysterious force play such a crucial role in the formation of our universe? First, it is important to remember that the universe in its early stages was a sea of particles and radiation. Amidst this chaos, dark energy might have been present, but not in the way we understand it today. What changes occurred in those initial moments that could have altered its nature and influence? Some scientists theorize that during that primordial period, dark energy might have acted more intensely or even had different properties. But how can we know if we have no access to such remote times? Current models suggest that dark energy, as we know it, began to dominate the universe long after its birth. But why did this change occur? What triggered it? The answers to these questions are at the center of an intense debate in the scientific community. Some researchers propose that in the early moments, dark energy might have been almost non-existent, or perhaps even repulsive, which would have led to a rapid expansion of the universe. The transition to the dark energy we know today could have been a crucial event, but what does this mean for our understanding of the cosmos? Imagine that the universe in its beginnings was like a balloon that is inflating rapidly. In that process, dark energy might have played a role in regulating that expansion. However, as the universe cooled and expanded, that influence may have changed, transforming into what we now identify as dark energy. As the universe expanded, the interactions between matter and dark energy could have created a delicate balance. What if this balance was what allowed galaxies to form and evolve? However, since we do not have access to those primordial conditions, we face a monumental challenge. How can we test these ideas? How can we unravel the mystery of dark energy in its youth? Modern cosmology attempts to study those moments in time through simulations and theoretical models. These tools are like scale models of a large building that is still under construction. They provide us with clues about how dark energy might have behaved. But there always remains an air of uncertainty. It is like trying to assemble a puzzle without having the complete picture on the box. The pieces are there, but how do they fit together? Furthermore, some theories suggest that the properties of dark energy may have changed over time. But what does this mean for the future of the universe? If dark energy is not constant, then its effects on the expansion of the cosmos could be unpredictable. Imagine a universe that behaves differently at different times. Are we prepared to accept that the cosmos could be a place in constant change, even at its most fundamental levels? Another intriguing aspect is the role of gravity in this context. In the early universe, gravity was in a different state, and dark energy might have influenced how matter was distributed. So the question arises, how is gravity related to dark energy in those initial moments? The interaction between these two forces could have been key to the formation of large-scale structures such as galaxies and clusters. As we continue to investigate, it is essential to keep an open mind. Dark energy is an enigma that requires new ideas and approaches. Could there be other factors or forces involved that we do not yet know? Science advances when we challenge our assumptions and seek answers beyond the obvious. In this sense, every new observation or discovery can offer a glimpse of light on the dark mantle of dark energy. Ultimately, the quest to understand dark energy in its beginnings is a journey that takes us deep into cosmology. It invites us to question not only what dark energy is, but also how it has shaped our universe and how it will continue to do so in the future. On this path filled with unknowns, every answer we find leads us to new questions, fueling our curiosity and passion for the cosmos. Dark energy, though invisible, connects us with the most basic forces of the universe. Its study is not only crucial for cosmology, but also reminds us of the fragility of our knowledge. Each advance in our understanding brings us a little closer to unraveling the mysteries of the cosmos. And perhaps one day we will discover not only the origin of dark energy, but also its true role in the history of the universe. So, as we continue to look toward the stars, let us remember that every mystery solved can lead us to another, even deeper one. Dark energy, with its enigma and potential, invites us to keep exploring, to keep questioning, and above all, to keep marveling at the vastness of the universe that surrounds us. Where does dark energy come from? This is one of the most intriguing questions scientists are asking today. Although it is believed to represent approximately 70% of the universe, its origin remains a mystery. Why is there so little information about something that seems so fundamental to the structure of the cosmos? The answer may be related to the very nature of dark energy. To better understand this mystery, It is important to consider how dark energy relates to the concept of quantum vacuum. This is where a fascinating question arises. Could dark energy be the result of fluctuations in the vacuum of space? The quantum vacuum, which is actually not empty at all, could be generating a form of energy that we cannot directly observe. But why can't we see this energy? The answer seems to lie in the way we interact with the universe. As scientists attempt to measure the energy of the vacuum, they encounter a problem. Theoretical models predict that the amount of vacuum energy is immense, far greater than what has been observed. What does this mean for our understanding of the cosmos? Perhaps in this mismatch lies the key to understanding dark energy. But how can we reconcile these vast differences between theory and observation? Some researchers have suggested that dark energy could be related to the existence of exotic particles that we have yet to discover. But what if these particles existed in a state that we cannot detect with our current tools? The idea that there is more to the universe than we can perceive is both fascinating and daunting. What other secrets might be hidden in the vast ocean of the cosmos? Another intriguing aspect of dark energy is its apparent homogeneity. Unlike matter, which clusters into galaxies and stars, dark energy seems to be uniformly distributed throughout the universe. Why this peculiar behavior? This homogeneous distribution raises questions about how dark energy formed and evolved over time. Is it possible that in the early moments of the universe, its behavior was different? For some, the key to unraveling this mystery may lie in the study of gravitational waves. Could these waves carry information about dark energy? The possibility that other cosmic phenomena reveal clues about its nature is an emerging field of research. Gravitational waves, which are disturbances in space-time caused by massive events, could contain secrets that help us understand how dark energy has influenced the evolution of the universe. As we delve deeper into the relationship between quantum vacuum and dark energy, another question arises. Could dark energy change over time? This idea, known as quintessence, suggests that dark energy is not constant, but may have varied throughout the history of the universe. How would this affect our current theories about the expansion of the cosmos? On the other hand, understanding dark energy also leads us to explore the connection between its quantity and the structure of the universe. Why does it seem that 70% of the cosmos is made up of something we know almost nothing about? This mismatch between theoretical predictions and observations is a challenge for cosmologists. Perhaps in this discrepancy lies a new physics that we have yet to discover. Meanwhile, the implications of dark energy also lead us to question the future of the universe. If dark energy continues to dominate, what fate awaits the cosmos? Some theories suggest that we might be heading towards a big rip where the expansion of the universe accelerates to the point of disintegrating everything we know. This idea, while frightening, is also a reminder of how little we know about the cosmos. Finally, it is essential to ask, how can we continue to investigate and unravel these mysteries? The answer may lie in collaboration between different scientific disciplines, improving our observational tools, and, above all, in human curiosity. The quest for answers about dark energy is not just a scientific issue, but an adventure that takes us to the very heart of existence. Each new discovery in the field of cosmology brings us one step closer to understanding dark energy. However, as we progress, we also find that each answer raises new questions. Dark energy is a reminder that the universe is a place full of mysteries, waiting to be explored. In this journey, curiosity and creativity are our best allies. How far will this quest for knowledge take us? Only time will tell. The vast universe around us is filled with enigmas, and one of the most intriguing is the mystery of cosmic voids. What are these enormous, almost empty spaces in our universe? Imagine regions in the cosmos where there is a notable absence of galaxies, where silence and solitude reign amidst the vastness. Why do they exist, and what role do they play in the structure of the universe as we know it? The existence of these voids raises fascinating questions. Could they be connected to dark energy, that mysterious force that seems to influence the expansion of the cosmos? In the search for answers, scientists have begun to investigate the relationship between these voids and dark energy. And the results are as intriguing as they are perplexing. It has been observed that cosmic voids tend to be larger than one might imagine. Some of them extend for hundreds of millions of light years. How is it possible that these enormous areas exist with practically no visible matter? What does this mean for our understanding of the universe? The astonishing thing is that these voids are not just empty spaces. They also seem to be shaped by the very structure of the cosmos. One fascinating aspect is how these voids may be related to the distribution of matter in the universe. In a homogeneous and uniform universe, we might expect matter to be distributed more evenly. However, cosmic voids seem to challenge this idea. Could it be that dark energy is creating an effect that favors the formation of these voids while simultaneously pushing galaxies toward other regions of space? Research also suggests that dark energy could be influencing the dynamics of these voids. As the universe expands, dark energy acts as a force that affects matter. But how does this happen exactly? Could it be that dark energy is manipulating gravity in such a way that allows for the creation of these vast empty spaces? Some wonder if cosmic voids could be a manifestation of dark energy in action. In other words, could these voids be the result of dark energy creating areas where matter cannot accumulate? This could offer a new perspective on how we understand the relationship between matter and energy in the universe. However, the connection between cosmic voids and dark energy remains a mystery. Some scientists argue that while voids are fascinating, their relationship with dark energy is not entirely clear. Could they simply be a feature of the universe that has nothing to do with dark energy? Or on the contrary, are voids an indication that dark energy is playing a much more active role than we think? The exploration of these cosmic voids also raises questions about the formation of structures in the universe. How is it that galaxies group into filaments and clusters, leaving enormous voids between them? This distribution does not seem to be random. Instead, it suggests that there are forces at play that are influencing the evolution of the cosmos. It is possible that dark energy is controlling the expansion of the universe in such a way that favors the creation of these voids. But what does this mean for the future of the cosmos? It could imply that as the universe expands, these voids will become even more prominent, leaving galaxies more isolated. As scientists continue to investigate, it becomes evident that cosmic voids are not mere empty spaces. They are essential components of the structure of the universe. Are we facing a new way of understanding how dark energy and matter interact in a constantly expanding cosmos? Each discovery about the voids brings us one step closer to unraveling the mystery of dark energy and its impact on our universe. In conclusion, the study of cosmic voids not only offers us a glimpse into the complexity of the cosmos, but also highlights the need to continue exploring these mysterious connections. As we delve deeper into the secrets of the universe, each answer may lead us to new questions, and each void may become a window into the unknown. Dark energy and cosmic voids are part of a larger puzzle, one that is still waiting to be completed. Is it possible that dark energy is not constant and that in fact it changes over time? This is the concept behind an intriguing hypothesis called quintessence. But what does this really mean? The idea that dark energy might not be a static phenomenon, but something dynamic, raises many fascinating questions about the nature of the universe. First, let's consider what quintessence is. In ancient Greece, this term was used to describe a fifth element that complemented the four classical ones: fire, air, earth, and water. In modern cosmology, quintessence refers to a type of dark energy that could vary over time and space. But how could we know if this is true? The theory suggests that just like matter and energy, dark energy could have properties that change depending on the conditions of the universe. What implications would this have? If dark energy can change, that would mean that the expansion of the universe might not be a uniform process. There could be moments when the universe expands faster or slower, but how could we measure something like that? Scientists have been trying to find out if there are signs that dark energy is in fact variable. Some studies observe the light from very distant galaxies to see if there are changes in the way they expand. Could the light from these galaxies give us clues about the behavior of dark energy? If we find evidence of variability, that could revolutionize our understanding of the cosmos. As we explore this idea, more questions arise. What factors could influence dark energy? Could the gravity of galaxies or the distribution of matter in the universe play a role in this? The interaction of dark energy with matter might be more complex than we think. Are we facing a phenomenon that challenges the laws we currently know? The possibility that dark energy is variable also leads us to consider its origin. If it behaves differently in different epochs of the universe, we might be looking back in time to understand its evolution. What was dark energy like in the early moments of the universe, and what role did it play in the formation of the structures we see today? The idea of a quintessence field also invites us to think about the future of the universe. If dark energy can change, does that mean the fate of the universe could also change? There could be scenarios in which the universe expands indefinitely, or perhaps cools and collapses. What does the future hold for the cosmos if dark energy behaves differently over time? One fascinating aspect is that quintessence could be related to other cosmic phenomena. For example, the relationship with dark matter and gravity is a topic of great interest. Could there be a connection between the variability of dark energy and the formation of galactic structures? The way the universe organizes itself might depend on the changing nature of this mysterious energy. Scientists are also investigating the possibility that dark energy interacts with other fundamental forces. Could there be something in the dynamics of quantum physics that explains why dark energy is so different from what we see in our everyday world? The answers to these questions could open new doors in our understanding of physics, but not everything is simple. The idea of a quintessence field also poses challenges. How can we reconcile this theory with current cosmological models? The scientific community is still debating how to fit the variability of dark energy into the existing framework of modern physics. Each new piece of information can change the game. As we move forward in our quest for answers, it is crucial to remember that science is a constantly evolving process. The search for the truth about dark energy and its possible variability pushes us to question what we know and to explore beyond our limits. What unexpected discoveries await us along the way? Dark energy, in its essence, remains one of the greatest enigmas of the universe. The idea of a quintessence field reminds us that as we seek answers, we must also be open to new possibilities. Every question that arises opens a new horizon of research and discovery. This journey toward understanding dark energy and its variable nature leads us to a future full of mystery and wonder. The exploration of the cosmos is not only a scientific endeavor but also an invitation to reflect on our place in this vast universe. As we continue to search, perhaps one day we will unravel the secrets that dark energy has kept hidden for so long. Dark energy, that enigmatic phenomenon that seems to dominate most of the universe, presents a monumental challenge for scientists. How can we study something that we cannot see or measure directly at first glance? It may seem like we are talking about a chimera, a concept that escapes our understanding. But what if I told you that this mystery represents one of the most exciting frontiers of modern science? Imagine a vast ocean that stretches beyond what our eyes can see. In this ocean, there are invisible currents that influence everything that floats on its surface. Such is dark energy. Even though we cannot touch it or experience it in a laboratory, its impact on the universe is undeniable. But why have we not been able to reproduce or detect it directly? The answer may lie in the very nature of dark energy. One of the main obstacles is that, unlike other forces we know, dark energy does not interact with matter in the same way. Electromagnetic forces, for example, can be manipulated and measured in laboratories. However, dark energy, which acts like a kind of anti-gravity, does not offer us the same opportunity. Why? Because it does not emit light or radiation that we can capture. It's like trying to touch the wind. We know it's there, but we cannot see it or stop it. But what if I told you that some researchers are seeking new ways to understand it? The idea is that by observing the behavior of galaxies and large-scale structures of the universe, we could indirectly infer the presence of dark energy. However, this raises an intriguing question. Can we really trust the inferences we make from what we cannot observe directly? Some scientists believe so, but others are more skeptical. One of the methods being explored involves the search for gravitational waves. These waves, which are small disturbances in the fabric of space-time, could provide clues about dark energy. Imagine that every time a star explodes, waves are generated that travel through the universe. If we manage to detect these subtle echoes, we could gain information about how dark energy interacts with the cosmos. However, this is a path filled with uncertainties and technical challenges. Direct experimentation is therefore one of the great limitations in our understanding of dark energy. Science advances by leaps and bounds, but we are at a point where the available tools and technologies are still not sufficient to tackle this enigma directly. What would this mean for the future of our understanding of the universe? It could mean that we are still in the early days of a long scientific adventure. However, not all is lost. There are innovative proposals aimed at breaking current barriers. Some of these initiatives focus on the possibility of creating advanced computer simulations that model the behavior of dark energy in different scenarios. These simulations could help us visualize how it might manifest in hypothetical situations, which in turn could guide us toward more specific experiments in the future. But what if the answer to this mystery were closer than we think? Some theories suggest that by better understanding the quantum vacuum, we could unveil secrets about dark energy. The vacuum is not simply an empty space. It is a place full of potential and energy. Could it be that dark energy is a manifestation of that quantum vacuum? This connection could open new doors in our search. As we explore these ideas, we must also consider the consequences of our ignorance. If we cannot experience dark energy directly, what does that mean for our understanding of physics? Science often advances by taking steps forward and backward, adjusting theories as we gather more information. Dark energy is the kind of enigma that could lead to revolutions in our way of thinking about the universe. The scientific community is divided in its approach to tackling this mystery. While some focus on theory, others are more concentrated on observation and data collection. The combination of both strategies may be the key to solving this puzzle. And in the meantime, human curiosity continues to drive research and the desire to discover the unknown. As technology advances, so does our ability to detect phenomena that once seemed unattainable. With more powerful telescopes and innovative observation techniques, the horizon of our understanding expands. However, dark energy remains a challenge that reminds us that no matter how much we learn, there will always be more questions than answers. Ultimately, the impossibility of directly experiencing dark energy invites us to reflect on the nature of science itself. Is it enough to accept what we cannot see? Or should we continue pushing the boundaries of human knowledge? The search for dark energy is not just an attempt to understand the universe, but also a journey into the unknown that defines us as a species. So the next time you look up at the stars, remember that there is a vast world hidden behind what we can observe. Dark energy, with all its mysteries, challenges us to keep exploring, to keep questioning, and above all, to keep dreaming of what we do not yet understand. In this cosmic journey, every question brings us a little closer to the truth. And who knows, maybe one day, dark energy will cease to be a mystery and become a story to tell. Is it possible that there are dimensions we cannot see or perceive? What if dark energy, that mystery that seems to dominate the universe, is actually an effect of those hidden dimensions? The idea may seem straight out of a science fiction movie, but in the world of cosmology, these questions are very serious and relevant. Dark energy represents about 70% of the universe, and its nature remains an enigma. But how do hidden dimensions fit into all this? Some scientists argue that dark energy is not simply a form of energy acting on the cosmos, but could be a manifestation of phenomena occurring in additional dimensions beyond our three-dimensional understanding. Imagine a universe where there are more than the three dimensions we perceive. In that case, dark energy could be the result of interactions that escape our perception. Have you ever wondered why the laws of physics seem to be the same throughout the universe? This fundamental principle, known as uniformity, could have a connection to these additional dimensions. If dark energy is the effect of forces or particles in dimensions we cannot observe, it could be influencing the expansion of the universe in ways we do not yet understand. But why is it so difficult to detect? The answer may lie in the way we interact with our environment. In our everyday world, we are accustomed to seeing and measuring things that manifest in the three dimensions we know. But what about what lies beyond? Hidden dimensions could be acting subtly, affecting the structure of space-time without us realizing it. This raises the intriguing possibility that dark energy is not an isolated phenomenon, but a window into a much broader and more complex universe. Imagine that there are forces and particles in those dimensions that we have never been able to observe. Could they be responsible for the acceleration of the universe's expansion? Some theoretical physicists have suggested that dark energy could be a byproduct of these interactions. If this is true, what we consider dark energy might just be the tip of the iceberg of a vast ocean of dimensional realities. And here arises a fascinating question. Could dark energy change over time? If it is indeed connected to hidden dimensions, its behavior may not be constant. This idea is presented in theories suggesting that dark energy could vary as the universe evolves, perhaps responding to changes in those additional dimensions. But what implications would this have for our understanding of the universe? Moreover, the concept of higher dimensions is not new. For decades, physicists have explored the possibility that there are more dimensions than we know. Theories like string theory suggest that subatomic particles are, in fact, tiny vibrating strings existing in multiple dimensions. If this is true, we could be living in a universe that is much richer and more complex than we ever imagined. The idea that dark energy is related to hidden dimensions could also offer answers to some of the most perplexing paradoxes in cosmology. For example, why does the universe appear to be so uniformly distributed on large scales? If dark energy acts differently in dimensions we cannot see, it could be playing a crucial role in the formation and distribution of the cosmos. Not only that, by considering these additional dimensions, we open ourselves to new ways of understanding how the universe behaves. If dark energy is linked to a broader reality, we might discover mechanisms that help explain phenomena that have so far remained in the shadows. The search for answers could lead us to rethink our current theories and open new frontiers in physics. However, the challenge persists. How can we study something we cannot see or measure directly? This is one of the most complex issues facing scientists today. Hidden dimensions could be completely inaccessible to current technology, making the investigation of dark energy even more intriguing. But that does not mean research will stop. On the contrary, each discovery in the realm of cosmology could bring us one step closer to understanding this enigma. What if, in the not-too-distant future, we could find a way to access these hidden dimensions? Imagine the impact it would have on our understanding of the universe. We could answer questions that have puzzled scientists for centuries. Dark energy could reveal fundamental secrets about the nature of reality itself, and along that path we might discover that what we consider reality is just a small part of a vast and mysterious set of dimensions. Ultimately, the connection between dark energy and hidden dimensions is not just a scientific question. It also invites us to reflect on our own existence in the cosmos. It reminds us that despite all our advancements, there is still much to discover and understand. Each mystery solved opens the door to new questions, and in that process we continue to expand our understanding of the universe and ourselves. The search for truth is endless, and each discovery brings us closer to unraveling the secrets that dark energy guards so jealously. What makes the universe in its vastness constantly change? One of the most intriguing questions in current cosmology is, why did dark energy, that mysterious force that seems to be pushing the universe to expand, begin to dominate just in the present era? This phenomenon has left scientists perplexed, and the search for answers leads us to explore cosmic time in a completely new way. Imagine a young universe, full of chaos and energy. In its early moments, gravity dominated the scene, attracting matter and forming the first structures. But what happened next? As the universe began to cool and expand, matter and radiation lost their prominence. However, at some point, something changed. What occurred for dark energy to emerge as the dominant force? Researchers have proposed various theories to explain this shift in dominance. One of the most fascinating hypotheses suggests that dark energy was not always the main player. In the past, gravitational interactions of matter were much more significant. But when and why did this balance break? Scientists are trying to unravel this mystery, and each answer seems to generate even more questions. Some studies suggest that dark energy began to manifest more prominently around 5 billion years after the Big Bang. But why exactly at that moment? Was there a trigger, a cosmic event that prompted this change? The theories range from changes in the density of the universe to the possibility that dark energy has properties that evolve over time. Additionally, there is the question of acceleration. Today we know that the expansion of the universe not only continues but is accelerating. But why did that acceleration begin at a specific time? If dark energy is constant, as some suggest, then why hasn't it been so from the beginning? This enigma leads us to question our understanding of time and space. An intriguing aspect of this discussion is that in cosmology, time is not simply a straight line. Cosmic events can influence each other in ways we do not yet fully understand. Could it be that dark energy, in its essence, is interconnected with the events of the universe in ways that escape our current understanding? The relationship between dark energy and time is one of the great mysteries that persists in scientific research. Moreover, some suggest that the universe may have gone through phases of dominance of dark energy and normal energy, meaning that this balance could be more dynamic than we think. If so, how can we measure and understand those changes? What tools do we need to unravel this cosmic enigma unfolding before us? The paradox of dark energy and its relationship with time also raises questions about the future. If dark energy continues to dominate, what will happen to the universe in the coming billions of years? Over time, could it lead to a scenario where the universe expands so much that galaxies drift apart until they disappear from our view? The future of the cosmos is intertwined with the nature of dark energy and its evolution over time. Some scientists venture to suggest that if we understand how dark energy began to dominate, we might glimpse not only the future of the universe but also gain clues about its origin. Could this knowledge lead us to rewrite the history of the cosmos as we know it? With each discovery, we are closer to answering these questions, and human curiosity continues to drive our quest for truth. Cosmic time is not just a concept, but a fabric that encompasses everything we know. As we advance in our exploration of the universe, it is essential to remember that each answer opens the door to new questions. Dark energy is just a part of a much larger puzzle, and understanding its relationship with time is key to unraveling the secrets of the cosmos. On this journey through the mysteries of the universe, we cannot lose sight of the importance of ongoing research. Each new finding brings us a little closer to understanding the role of dark energy and how it has shaped our universe. Perhaps in the future, we will be able to look back and see how each piece fit into this vast cosmic puzzle. Dark energy is a reminder of how little we know about the universe. It invites us to keep exploring, to question our assumptions, and to remain open to new possibilities. Ultimately, by delving into the enigma of cosmic time and dark energy, we might discover not only the fate of the universe, but also our own story within it. Einstein's cosmological constant is a fascinating concept that leads us to explore how great thinkers of the past have influenced our understanding of the universe. How is it that an idea that originated over a century ago remains relevant today? To understand this, it is important to go back in time and immerse ourselves in Einstein's own thinking. In 1910, while formulating his theory of general relativity, he realized that the universe could not be static. At that time, the prevailing view was of an eternal, unchanging cosmos. However, Einstein suspected that there must be a force that maintained the balance between the gravitational attraction of galaxies and a possible expansion of space. What if that force existed? To resolve this dilemma, Einstein introduced the cosmological constant, a term he added to his equations to allow the universe to remain in a state of equilibrium. But the story doesn't end there. When Edwin Hubble demonstrated in 1929 that the universe was expanding, Einstein realized that his cosmological constant had been a mistake. In a famous twist of fate, he came to refer to it as his greatest mistake. But could he have been wrong to dismiss it? In the 1990s, astronomers made a surprising discovery. The expansion of the universe was not only continuing but accelerating. This finding led scientists to reconsider the cosmological constant, now interpreted as a form of dark energy permeating space. Could it be that what Einstein had discarded as a mistake was in fact the key to understanding the behavior of the universe? The idea that the cosmological constant could be responsible for the acceleration of the cosmos's expansion is a concept that has generated renewed interest and significant debate. But what exactly is this cosmological constant? Broadly speaking, it is a measure of the energy density of the vacuum of space. Essentially, it could be seen as a kind of pressure that acts in opposition to gravity. As galaxies move away from each other, this pressure helps accelerate their movement, ultimately affecting the structure and evolution of the universe. However, despite its apparent simplicity, its exact nature remains a mystery. Scientists face a dilemma. Models predict a vacuum energy amount that is thousands of times greater than what we observe. Why is there such a discrepancy? The cosmological constant should be a fundamental part of our understanding of the cosmos. But we have yet to measure it accurately. Could it be that there are other factors at play that we do not yet understand? Some theorists propose that the cosmological constant might not be constant at all. What if, instead of being a fixed value, this dark energy fluctuates over time? This idea that dark energy could change throughout the life of the universe opens up a myriad of questions. How would this affect the formation of galactic structures? Could it even alter our cosmic destiny? Einstein's cosmological constant prompts us to reflect on the role of great thinkers in science. Sometimes an idea that seems wrong can become crucial in the future. How many brilliant ideas have been discarded because they did not fit the knowledge of an era? The history of the cosmological constant reminds us that scientific advancement is a journey filled with unexpected turns. In the current context of cosmology, the cosmological constant has become a pillar in the quest to understand dark energy. But will it be enough to unveil all the secrets of the universe? Research continues, and with each advance we get a little closer to unraveling these mysteries. The cosmological constant may be just the tip of the iceberg in our exploration of the cosmos. The story of the cosmological constant also raises a deeper question. What does it really mean to understand the universe? If dark energy is a fundamental part of the structure of the cosmos, then we are compelled to question our interpretation of reality. Are we ready to accept that there are forces at play that escape our current understanding? As we continue to investigate, the cosmological constant reminds us that scientific knowledge is an evolving process. Each discovery opens new doors but also raises more questions. What other secrets will the universe reveal to us if we keep probing? Einstein's cosmological constant is a reminder that, although sometimes our mistakes may seem like failures, they can be the path to great discoveries. So the next time you look up at the starry sky, remember that there is much more than meets the eye. The cosmological constant invites us to keep exploring, to question, and to marvel at the mysteries that still surround us. In the vast universe, each question opens a new chapter in our quest for knowledge. What mysteries will be revealed in our next cosmic adventure? The answer remains in the air, waiting to be discovered. Dark energy is an enigma that invites us to reflect on the very nature of the universe. What is this phenomenon that constitutes approximately 70% of our cosmic reality? Many questions revolve around this mysterious component, and each answer leads us to more inquiries. Why, despite its great influence, do we know so little about it? Every time we look at the sky, we witness the dance of galaxies, but we are also witnessing a force that accelerates their separation. As we explore the vast cosmos, dark energy presents itself as an enigmatic character that challenges our understanding. How is it possible that something we cannot see or measure has such power over the expansion of the universe? The answer to this question leads us to think about the nature of the invisible. That which does not emit light or radiation yet has significant weight in the fabric of the cosmos is a reminder that there is much more beyond what our senses can grasp. Let's consider the future of the universe. What will happen if dark energy continues to dominate? Theories suggest that we could face a fate where the cosmos expands eternally, or even an apocalyptic scenario known as the Big Rip. Could dark energy be responsible for such a dramatic end? The possibilities are as diverse as they are unsettling. Each new discovery offers us a glimpse of what the future may hold, but also reminds us of how little we truly know. On our journey, it is crucial to ask, why does dark energy seem so homogeneous in its distribution? This mystery of homogeneity leads us to question how this force behaves in the vast expanses of the universe. Throughout history, scientists have attempted to unravel this enigma, but each attempt reveals more about the limitations of our knowledge. Is it possible that there are cosmic principles we have yet to discover? Furthermore, the relationship between dark energy and dark matter leads us to another series of questions. If both are interconnected, why can't we clearly identify their link? Dark matter, which makes up a significant part of the universe, seems to be the perfect complement to dark energy, yet their interaction remains an unresolved mystery. Could it be that these two forces are two sides of the same coin? As science advances, we face new theories, such as the quintessence field, which proposes that dark energy is not constant but changes over time. This opens up a range of fascinating possibilities. If dark energy can evolve, what does that mean for the history and future of the universe? Each theory is like a piece of a puzzle that invites us to keep searching for the complete picture. However, the true difficulty lies in the very nature of dark energy. Why can't we replicate or measure it in our laboratories? The impossibility of experimenting with this force confronts us with the limits of our understanding. Perhaps the key to unraveling this mystery lies in our ability to imagine and formulate new hypotheses. Each attempt to understand it pushes us to explore beyond the known. And what about the energy of quantum vacuum? This intriguing connection between dark energy and the properties of vacuum could be the clue we have been searching for. But why is it so difficult to establish a tangible link? Quantum physics is a field full of surprises, and each discovery pushes us to rethink what we believe we know about reality. The mystery of cosmic voids also offers us fertile ground for speculation. These vast regions of space seem to be connected with dark energy, but how? The search for answers in these nearly deserted areas of the universe could reveal patterns and connections we have yet to imagine. What secrets lie hidden in the darkness of the cosmos? In the end, Einstein's cosmological constant, which was initially discarded, returns to the conversation about dark energy. Why has an idea he himself rejected earned a place at the center of our current study? This twist in scientific history reminds us that, in the pursuit of truth, sometimes we must return to the questions we thought were answered. Dark energy, with all its complexities, offers us a unique opportunity to reflect on our position in the universe. Do we really understand what surrounds us? Each mystery we unravel opens the door to a new world of questions. The exploration of dark energy is a never-ending journey, a path that invites us to marvel and to question. Ultimately, the true mystery lies not only in dark energy itself, but in our capacity to continue probing, learning, and above all, dreaming of what is yet to be discovered.